Okay, so welcome to the next session. So we have a talk and then a discussion. So the talk will be by Patrik Jansson and about dimension analysis and graded algebras.
Yes, thanks. This is joint work with Nicola Botta at the Potsdam Institute for Climate Impact Research in GM Silva, who will come to join us for a PhD, I think in January. And it's work in progress. It's not something, we're aiming at a paper, but we haven't sort of finished it. And there is an interesting mix of Idris and Agda code in the repository, because Nicola Botta is used to Idris, and it's actually Idris 1. And I'm more used to Agda. And then to complicate matters, VM is more used to Nicola Agda. So we have actually 3 different sort of partial files of different things which don't sort of work together. So talking about interoperability of provers and so on is a relevant topic in our group. So, okay. This is not going to be any big advanced Agda things, but it's more like about what is, it's more of a tutorial on dimension analysis and how to code this up. So,
I'm sorry, could you make the font just a tad bigger?
The font bigger? Yes, I guess so. How much bigger?
That's good, thank you.
Let's hope it fits.
Yeah, any more than that probably doesn't fit.
Okay, so first of all, this is just sort of defining the different topics that are, or the different types that are relevant in dimensional analysis. So first there are sort of physical quantities, and these are usually assigned a dimension. So informally there is some kind of function dim which takes a quantity of type Q to some type D for dimensions, and we'll later make it an index type, so it's Q of D instead.
And maybe these lights could be turned on?
Lights, yeah. Anyone knows how that's done?
Anyone know this lecture?
It's hard to read because it's too stuffy.
I don't know.
Oh, look. Yeah.
It seems like there's something here, but I don't know which one is.
Press a random button and see.
You can turn them on or off. I don't think you can turn them like lower.
Nice.
Do you want one?
Oh no, it's terrible.
Yeah, the switch is open or push.
Maybe we could just turn them off.
It's
better? It's much better,
Yeah.
Okay, so anyway, this is the classical things like you've got length, speed, force, and so on, and they're usually measured with respect to some system of units. And you usually have one unit per base dimension. And just to clarify the terminology here, so we want to capture a certain group of physical things, and for geometry, for example, it's not enough with one base dimension, length, and then you get area and volume and so on by squaring in the power 3. Kinematics, so things which move, but in sort of the ideal sense, no mass and so on, then we have the class LT of things which has 2 dimensions, a length and a time dimension. And then for mechanics, then we have LTM, length, time, and mass, and so on. And if you have got electromagnetics or you have different things, and you have more and more dimensions. But it's often useful to sort of focus on a few dimensions that you actually need for your problem, and then work in that class of physical systems. So, okay. Usually if you look at physics book or so on, then when they talk about dimensions, or even the sort of classical book by Barnblatt about dimension analysis, they say things like acceleration has dimension L over t squared. So, and they say, sort of formal reading there would say would be, there is a function, lambda LTM to L time over t squared. So this is the dimension function. And what do they mean there? Well, actually, it describes how the measured value, now maybe I should go one step back in size so I fit my last character on the line. The measured value, how does that change if you change the basic units of measurements? So if we divide our length scale by 10, then the amount, the acceleration value that we get will be 10 times bigger. And this is easier if you start with a simpler case of just dimension length. So if my length here is 1.78 meters. If we then divide the unit from meters to centimeters, we divide the unit by 100, then the length, the value of the length will be 100 times bigger, so it's 178. So this is sort of a trivial observation, but it's sort of the same kind of thing that happens with transfer formations of bases and linearity and so on. So if you change the base, then you also change the value of the coefficient. So if you divide your base vector by 10, so it becomes a very small base vector, then all the coefficients will be 10 times bigger. And another way of saying that is that, well, I should expand this. The height is actually invariant. The height, I have a certain height. It's this high. And the system of units measuring that will determine what the value I will assign to it. So if I measure it in the times of mobile phones, I get one number, and centimeters another number, and so on. You could think that you need a measuring rod for every kind of dimension, like acceleration has one measuring rod and speed has one measuring rod and so on, but it works better if you decide to focus on one measuring rod per base dimension and then just multiply those together to get the measuring rods to standard units for other dimensions. So for example, then if you have something with a more complicated dimension like area, so if we change the linear scale by dividing by 10, the area will be multiplied by 100. So the area unit is 100 times smaller. And generally speaking, if we have a system with length, time, and mass, and we change all three of them, so we divide the unit of length by L, time by T, and the mass measurement unit by M, then acceleration would scale as L over T squared, and force would scale as m times L over T squared. So that's like the formal definition of what the dimension is supposed to be doing. And of course, this choice of dividing the unit and multiplying the other, we could go in the other direction, but this is a standard way of describing it. If we make the unit of measurement smaller, how much bigger is the measured value? So when we have an equations like the classical force equals mass times acceleration in physics, the dimensions must match up, and you could say that's sort of, if you have this dimension function which takes a quantity and just extracts its dimension, then the dimension of f should be equal to the dimension of m times a. Similarly for addition, subtraction, and so on, you have to keep the dimension constant in the expression. But for multiplication itself, we don't have that. So as you know, if you multiply the length by a length, you get an area. So we actually also multiply the dimensions. We have homomorphism here. The dimension of m times a is the dimension of m times the dimension of a. So how do we type this then? I'm trying to build this up step by step to see what we need, and at the end we have a full structure. So we need to be able to multiply that they divide the dimensions as well as the quantities. So let's start with some dim stuff. So I just sort of naively start with a record type here which collects things I need for talking about dimensions. So there is a type of dimensions or a set of dimensions, dim. There is some things are dimensionless, so that's a base value, like 1 or 0. And then I described it as a multiplicative way. I can multiply dimensions and divide dimensions. And I can also take, well, repeated multiplication and division, so I can take a dimension to the power. And this is, I mean, there's some skip details that I define these things. So we'll get back to the laws later. I will not define them, but it does see what they ought to be, and the concrete implementations in the example of LPM. And do ask those questions on the way. So anyway, this is sort of a specification. I haven't sort of filled in any concrete implementation yet, but just to have something in place. We need multiplication, division, dimensionless thing, and over a set of dimensions. Okay, let's see. So the quantities then should be something that is indexed over these dimensions. So this is again a record. Actually there are two things needed. I need to index by dimensions, but I also need some scalars to measure the size of the quantity. So if I now have increased the font so much that I need to scale it up.
Any chance you can load the code so that we get syntax on it?
Yeah, I can either load the code or use the org mode. So I actually,
Ooh.
the thing is that I have loaded the code in a copy of the file, which is just here. So if you want to see quantities, so this is one way of doing it. I'm not sure how much fits now with this font size. But, yeah, maybe let's look better. Yeah, there are two screens. Kind of different from the two screens.
I think now that the light's been dimmed, you can put the font size back down. Really big problems on contrast.
Yeah, I can reduce a bit here. Anyway, so the key here is that we have some types of quantities indexed by the dimensions, which we have sort of started specifying. We have a dimension function for convenience that we can extract the dimension index from a quantity. And then we have some different operations. And we start with these three. We have a zero quantity, we have addition, and we have scaling. So the name here is just because we can actually look at quantities within a certain dimension as a one-dimensional vector space. So they are sort of trivial vectors, boring vectors, but you can sort of, and that works well with this system of units thinking and so on. So the vector space has a base vector, and that's like the measuring rod. And then you get a coordinate, and you can scale these things. Okay, so that's the first part of this Q stuff. But it has a little more structure. It's almost a field, I say. So we have sort of a ring, we have a 1 and a multiplication. So 1 is a dimensionless quantity, and multiplication takes arbitrary dimensions d1 and d2 and multiplies the indices. So length times length is then of dimension length squared, which is area, and so on. And similarly for division. So if I divide quantities, I need to divide the corresponding dimensions as well. So you can see that the dimension index tracks the operations performed. And if I'm at skip, I can.
By field, did you mean group? I mean, this display group over another group, right?
Yeah, so I will get into actual structure, but yes, the dimensions is an abelian group, and the Q's are going to be a graded algebra or a graded field over that group. That's the sort of mathematical structure. And that's what I'm saying here. That the algebraic structure space is an abelian group for the dimensions, and in practice, now, for example, if you use the LTM class of physical quantities, of physical phenomena, then we have 3 base dimensions for length, for time, and for mass. So we can represent this group by 3 sort of base vectors, L, T, and M. And I implemented that as a concrete example. Yeah, maybe I should now open the other one, because it's more L, T, M. So a dimension is just a vector of 3 integers. So of course 3 would be some other number if you had more base dimensions, but just here for concreteness. So dimensionless is just a vector of 3 zeros. So that's now it's not the vector space of the quantities, now it's a vector of basically the coefficients in front, or the exponents to L, T, and M in the dimension. How many times I multiply them. So if we have a free abelian group, that's basically just the base values LTM to the power of some integer multiplied together. That's all that contains, that's what the vector of integers represents. So I can multiply dimensions, and I have somewhere additional vectors that I imported somewhere, and subtraction of vectors. So the exponents, when I multiply two things, the exponents of these monomials that I sort of, the dimensions you should describe as, I will just added or subtracted. And as I said, this is the 0 vector, and then we have this L, T, and M. Of course, it's an arbitrary order. I just have to pick So let's see why I'm in the.
Another way to view this is that these are the normal forms of your dimension expressions. Right?
Yes. Yeah, so I mean, I could have a syntax tree for dimension expressions, and this is like the natural normal form. As I said, it can be described as a free abelian group over the three generators. And that can be represented as a vector of three integers, which are the exponents of these three components. How many times positive or negative you use them in your multiplicative expression. That's yes. Okay, Q record type, and I guess I should go to L and Q. Sorry for the mixing back and forth here, but this is perhaps prettier. So the Q data type is trivial. It just is a new type around a value of some scalar underlying type S. So it has, I mean, there's some garbage text around it, like record and constructor and field and val and so on, so you can put in and extract this value, and you're not supposed to use those constructors and destructors elsewhere, just in this core implementation of the units. Then you're supposed to treat this abstractly. So this is then a concrete implementation of one of these things I called Q stuff about. So this is a type, this dimension function, and then, not surprisingly, the zero quantity has just a zero inside it. Addition is addition, scaling is multiplication of the underlying scalar data type, and also multiplication. I mean, the unit is 1. I call it 1Q here, just to keep track of what's what. Multiplication just multiplies the scalars and divides the scalars. So the only interesting thing here with respect to the underlying scalar type is that I have indices. So this is a gradient structure. And as you see, I can have any dimension d1 and then the dimension d2, and then I combine them together. So, and then it says skip, so I guess I should go back here because that's easier to skip. Yeah, the one-dimensional vector field, graded field, and then, yeah, discussion, field or not a field. So, first then, the operations I need, as for physical quantities, they use division, multiplication, and so on. So I need a field underlying. So we need a scalar field S, and that is sort of lifted into the scalar field when the dimension is dimensionless, so basically 0. But not for other elements. So just to exemplify, to be extra careful here, if we want to multiply a length by a length, we get an area. So it doesn't stay within the same type. So the multiplication for this graded field does not have type QD to QD to QD. Only, well, it has that type only if D is dimensionless. So otherwise, I take two values and then I dump in a third. Sort of, what do you call it? Fiber or index or whatever, yeah. they move around. So this is just to sort of clarify it. And then you can form the type of pairs, dependent pairs of a dimension and this, or more complicated structures, and then define the field structure on the whole, sort of forgetting all the, or combining all the indices and being one set. But we don't really want that because we want to keep track of this, because that's the strength of dimensional analysis. The fact you can say, well, this expression does not make sense already based on the types, but the dimensions. Okay, so one thing I haven't done yet is to measure quantities, because I was saying that yes, we have this constructors val and so on, but we're not supposed to be actually directly interacting with the quantities. We're supposed to measure them with a function called measure, and for that we need a system of units. So that's defined, a system of units. So that's a vector of as many scalars as you have base dimensions. So that's entailing this, how big they are supposed to be. For the LPM class here, I mean, n could be bigger for another class. And examples of a system of units would be the SI system of units, or the CGS system, where you measure things in centimeters, grams, and seconds. smaller things. There's also a system of units which is convenient for measuring very small things like Planck's constant. So now we can interpret this sort of syntactic dimension, this data type of 3 integers, into its dimension function. Remember, the dimension function was mentioned very early as the function that takes the scale factors for L and T and M, and then becomes some monomial, some exponents of these groups. So we can of course translate from one to the other. Maybe this is prettier than the other in fun. So the dimension function takes this syntax tree, syntax tree, I think not even syntax, this 3-element vector, and then becomes a function from a system of units to a scale. So, and it's just repeated exponentiation with power. So take the system of units and dimension, which is a vector of these coefficients. So L to the power of something times T to the power of something times M to the power of something. And then if you combine that, let's get this full screen here, then we can then get a number, a scalar number out of a quantity, of a physical quantity. So you measure a quantity Q by a system of units, and then you just take the dimension of Q, you translate it to the dimension function, you apply that to the system of units, then you get a scale factor for this particular dimension, and then you multiply it with the actual Q. And here is some shining through some abstraction barriers of the LTM Q dot Q dot 12. But measure is the one you're supposed to use elsewhere outside. You're not supposed to be using this above construct. Okay, example quantities. Yeah, skip code it says here, so I'll just do that then. So height is a length. My length was 1.78 in the SI system then. Acceleration, now we can see that first I define a value type dimension, which is L divided by T squared. And then I use that as the index for Q. So say 9.82 is usually what you consider the acceleration from gravity. And then exemplifying this SI system, well, that's 1-on-1, everything is sort of the base system I'm using. And then how do I define the values here? Well, this is, as I said earlier, this is what I divide the unit by to get to the system. So I divided meters by 100 to get centimeters. Another way of reading it is that 100 centimeters is 1 meter. So actually this is seconds, so I have meter. I should have put them, it's called, sort of explained in this order, but the middle one is actually in my case the second always here. So the second is unchanged. So the transformation from kilograms to grams is just 1,000, of course. Examples, I mean, my mass happens to be around 76 in the SI system, and then I can compute my weight, the force going down by multiplying it with G, and so on. So these things sort of work out as these computations go. And just to show that something is actually computing, there's a float module somewhere which doesn't have any nice properties, so I just postulated it's a field. Because I just wanted to have an example, and it's a bit impractical to use rational numbers with these bigger numbers. So anyway, my length is 178 in the CGS system, and apparently the force that I'm exerting on the floor here is 7.4 to the power times 10 to the power of 7. Because remember, this CGS system is a measure of very small things like centimeters and grams, and so all the numbers become very big. I should skip that. Oops, sorry. Dimension analysis, yes. So now we get to the more interesting part. Maybe I should go back to the other file. Because when it's more text, that's at least better. Yes? 5 minutes, yeah. So assume you have an ideal. So there's basically a point mass hanging from a piece of string of length x, it has a time period t, and you know you wake up in this closed room, you have no memory of anything, and you want to figure out if you're on Earth or in a spaceship accelerating some other. So they take a piece of string and they sort of try to measure out what the gravity is. So how do we measure the gravitational constants from the other four parameters? And then generally you say, oh shit, this is a complicated problem. It's like it's a function of 4 values, and then you should compute this gravity. It's the mass, the length of the pendulum, the time period, and then the dimensionless theta, the angle it starts from. So, well, pi theorem comes to the rescue. I'm not sure why it's called a pi theorem, but that's a classical theorem from dimensional analysis. And basically, in practice, what it says, you can simplify this function significantly. So first you identify independent dimensions. In this case, we got independent dimensions of mass. You can actually see this line there. Mass, length, and time. And actually, if you reason a bit about physical laws, it turns out that this gravity function is not really allowed to depend on how you measure mass, length, or time. So that means that basically you can reduce this whole function to a function of 1 variable instead of 4 variables. And I'm rushing the explanation here a bit, but basically you notice that you can compute the acceleration as a combination of this dimension function, which multiplies the way you measure time and the way you measure length by well, if you combine that with the generation, you get a dimensionless version of acceleration, and that's the only thing which remains. So this is actually, and now I come back to the algebra gravity, because this is my only hole to fill here. So the question is then, what is this monomial that could be in place for combining these measurements? And one interesting thing is here that I cannot use the mass here. There is no way I can use the mass. Because notice that mass has dimension, well, the mass has dimension mass, and acceleration doesn't involve mass. It only has length over time squared. So with the type rules I've got, I can't possibly use, I can take the power of m to 0, that's the only thing I can do with it. So I'm not allowed to use it at all. And then, okay, how can I use x? Well, actually, the only thing I can do with x to get an acceleration out, an acceleration has dimension length per time squared. So I must multiply by x. So if I do, this is multiplied by q and then something.
Move the underscores.
Oh, yeah, sorry. Before I refine it instead. Okay. So now, now we see why you might want to have a show instance for some of these things, because I have a q and a vector with some different things inside it. But if I now don't have time to go through the details, I can say, okay, actually t has to be taken to the power of -2. So let's instead divide by t to the power of with q and 2z. Let's see if I get this right.
Oh.
No. Let's take it step by step. So it's t to the power of something, and I'm pretty sure this should be, yes, I'm not sure why I didn't want to fit it before. Okay, but anyway, if you have ever had more time, I would sort of experiment with this a bit and say, basically, there's no choice here. The monomial has to be exactly x divided by t squared. Otherwise, it doesn't apply. So, yeah, implications, well, from a four argument function, we get the 1 argument functions, and if you want to do experiments to infer what this function is, it's much easier, of course, to infer a 1 argument function than a 4 argument function. And moreover, for small angles, this function doesn't even depend on theta. So it just becomes a constant, which happens to be 2 pi squared. But that doesn't come from dimension analysis. Okay, ending up. You can do dimension analysis. It's usefully expressed with domain types. Physical quantities form a field graded by a Mendelian group of dimensions. Other examples of things which are graded by something is tensors, which also physicists like to use. It might be interesting to see what happens with multiple gradings. I mean, should you rank your physical quantities by, should you make tensors first and then dimensions, or should they add dimensions first and then rank to make it tensors, or tensors of quantities or quantities of tensors, and so on. We haven't explored that part yet, but it's the same kind of structure. And yeah, the library code, as I said, is a little bit apparently a mix of Idris, Agda, and cubical Agda. We hope to converge on that in a month or two and submit a bit. Questions?
So there's also a notion of grading via like monoids or like groups, even if that's something you're interested in. So you could even combine. So this is for what you mentioned with tensors, right? You could combine your grading that you have with such a tensor grading, for example, into like one single grading structure. And then I think you don't necessarily have to answer the question, well, which grading do you do first, because you do both of them at the same time.
Yeah, you might take the product of the grading things and then grade with that one. But it's not obvious if they sort of conform to each other in the right way.
Yeah. Also, so you I think you called this a graded field. This sounds a bit strange to me because the addition doesn't preserve, like you can't add things of different with different rating, right? So like you don't have a total addition, even if you mentioned this idea of, well, you could wrap everything under an existential for the rating, but this doesn't work with addition, right? So
actually, I mean, in the when you talk about graded rings and graded algebras and so on, then you do so that you have this as an intermediate step, and then you take formal linear combinations of all the QDs as a type, and then you can add 3.
yeah.
And then this is the discussion about sort of fewer components in that one. So things which only live within one of the QDs.
Yeah. Okay, so
but mathematically, yes, you can recover the sort of field structure, group structure on if you just sort of smash it all together. I feel that's a little bit cheating and sort of trying to hide the element types there, but yeah, that's usually the way it's defined in the mathematics courses. Yep.
Yes, we have just a few dimensions on which you like generate non-possible, a few base dimensions on which you consider all the possible combinations. But I think a way to look at the general thing is by observing that one-dimensional vector spaces have some kind of a group structure with the real numbers tensor product and dual space. And then I guess the dimensions are just one-dimensional vector spaces.
I don't know. Sounds interesting.
Yeah, so I'm a bit afraid. I was surprised by this phantom type you're using. I mean, Q was a phantom type, I think. The dimension was only an index, but not whose otherwise. I wonder whether there's alternatives. So, for instance, you would think of that your bases, like either you have meters, kilograms, and seconds, or you have centimeters, and so on. And these would be like, you could organize them in a category and then as objects, and then your morphisms would be a base change, right? Yeah, then you would get a bit of a different formalization, I guess. Like the concept of a base change. I think you're basically we decided to have just this SI system as the universal, and then other unit systems are expressed by scalars over this SI system, right? The standard.
Yeah, but that's sort of I mean, what I call the base system is one. I mean, there has to be, I mean, there is a number stored somewhere in the computer, and that we have to decide on what measuring rod we use for that one. We can't completely abstract our way out of the world.
Well, yes, we have a vector space as an argument, and then also have a meter as an argument.
Yeah.
Fred?
Right, so it's nice. I have a comment and a question. The comment is that Colin McBride and I were thinking about similar things. We ended up with graded centerings as our model. I have a paper last year where we extended this to matrices that I can point you to. And the question is, so when we present this to metrologists, they usually bring up the problem of dimensionless units, where you might have different physical things that happen to have the same dimension, which is often dimensionless, such as radians and things like this, which isn't quite explained by the Abelian group structure. So do you have any thoughts on this?
Well, the thing is that what you call dimensions is your choice. So you can have sort of redundant dimensions as well. Then the pi theorem becomes much weaker because you have lots of stuff which could, because then scale factors come in, like, okay, how do you translate between these radians and these degrees and this number of shoes or whatever dimensions you have on the dimension of this sort of dimensionless thing. But there's nothing sort of stopping you from introducing more sort of base dimensions.
So during interactive editing, we saw a lot of riddle when you started filling in like the number. And I think that's because Agda is really bad at inverting the zip word function, or not the zip word, but the pointwise addition on vectors that you're using to combine the units. Do you think like we could make Agda better, or?
Maybe, I mean, I would say this code suffers from having been hand translated from Idris.
Right.
And then adding whatever I needed to get it to actually type check in Agda.
Right.
Because Nicola was writing the stuff in Idris and I was doing. So it's not a pretty code base. It's 5, which is the talk here. But yes, it is inconvenient. I mean, showing values when you're halfway down and so on is I mean, just providing a show function and having that being used in your normalized term, for example, would also be useful.
Well, I think here it couldn't even compute the.
Yeah, that would be the case, yes. But
yeah.
I mean, I haven't shown that here, but usually when it comes and you ask, okay, what's the dimension of this? And then it says, I mean, it gives a vector.
Right.
And the vector has integers, and the integers are like, you know,
-1,
2, and then, yeah. So you have to like scratch your head to even read out what the vector is, when it could just say LT squared m minus 2 or something like that, if you had like your own show function. Yeah.
How reliable is this pi theorem? Because in some formulas you have physical constants that have that dimension. That have a dimension. So you can convert time into distance by multiplying the speed of light, for example. So like this thing doesn't hold in general.
Well, I have yet to see an example. I mean, if you multiply by the speed of light, that has a dimension as well. So.
Right, but your pi theorem seems to exclude that you would use a quantity in one dimension when you need something of another dimension, but maybe you have a formula, a physical formula there that holds the constant.
Yeah, I mean, I haven't invented the pi theorem, which is a classical result from, I don't know, like, at least 50 years ago. And I mean, it sort of depends on the assumption that physical equations are sort of scale independent. And that's a special case of a sort of symmetry independence, which also used in other kinds of physics where it's not. I mean, here it's just scaling and so on.
Right, I think my question is maybe on the way you would use it to deduce what the formula would be.
Well, that one I think is solid and sound, so I mean, there's no problem there. Unless you got some symmetry breaking operations.
I mean, you can break symmetry by having a physical constant with the definition. So that's
We can take that one.
When you use the theorem, you have to decide what you want to consider, right? You want to say that the speed of light is one of the parameters you might depend on,
right.
and that goes into the theorem.
I also have another comment, which I realized that I think the pi theorem you're using, I mean, in some sense you could reduce this to a question of what units can I sort of combine from other units, like how many options do I have, and of course in your case it was unique, and maybe in other it might not be, but what you could do with this is of course write a tactic, for example, that looks at the units and says, well, I will just give you a term that satisfies those units if it exists, right? Because this is now basically a simple search problem. And it might be unique sometimes, and it might not be in other cases, but I think you could use this to actually find those values without actually having to design anything.
Yeah, sure. I mean, it's about linear independence and dependence, and you can just solve the equation system and infer what it should be. And it's also related to parametricity. I mean, there is this old paper from parametricity and units of dimensions of units. I don't remember exactly what it's called. So you get nice results if things are parametric or dimensions. Okay.
Okay, so Patrik again, thank you. So next we have a discussion about GH.